On Friday, we talked about graphs of exponential functions. So today we're going to talk about some applications of exponential functions, primarily interest earning formulas. So exponential growth occurs when a quantity exponentially increases over time. And the formula that you're going to want to think about is y equals a times 1 plus r raised to the t power, where a is your initial or your starting amount, so initial amount or starting amount, r is the rate, and that's going to be written as a decimal, and t is the time, and that's usually going to be in years. So the first example says the original value of an investment is $1,800. If the value has increased by 7% each year, write an exponential function to model the situation, then find the value of the investment after 15 years. So I'm going to use f of x for function notation, but you could just as easily use y. In my formula, my initial value goes first. So in this case, that's $1,800 or $1,800. 1 plus, then my rate is 7%. So as a decimal, that's 0.07. And my power is x, since I used an x here, or I could use a t just as easily. Then, to find the value of the investment after 15 years. So that's going to say f of 15, because that's the number I'm going to plug in, 1,800 times. Now, usually on a test, like a multiple choice test, you'll see that value already combined together. 1 plus 0.07 is 1.07. And then my power will be 15. So that's one of the big things you have to remember when you're keying this information into your calculator. Make sure that you use parentheses and make sure that you raise the base to a power. I'm closing my parentheses to the 15. And usually I have you round your answers to 2 decimal places. But again, we're dealing with money, so that again makes sense to round to 2 decimal places. So that's $4,966.26. And you're pretty much doing that throughout. So the second problem says in 2002 there were 972 students enrolled at Oakview High School. Since then, the number of students has increased by 1.5% each year. Write an exponential function to model the situation, then find the number of students enrolled in 2014. So my function, I'll call it f of t this time, t being time, equals. And again, my initial value goes first. So in this case, that's students instead of money. So 972 students. In parentheses, I'll have 1 plus my rate, and that's 1.5%, so 0.015 raised to the t power. So then I have to determine how many years I'm evaluating here. From 2002 to 2014, that's going to be 12 years. So I'm going to plug in a 12 for t, so 12 years is my time, 972, and then 1.015 to the 12th power. So again, to my calculator, 972, then in parentheses, 1.015 raised to the 12th power. Now, in this case, since we're talking about students instead of money, we typically just leave it at the nearest whole student. So that's going to be 1,162 students. So as long as you know your initial amount, your rate, and your time, you're pretty much all set. The next two examples, instead of talking about exponential growth, talk about exponential decay. And the formula is very, very, very similar. Y equals A times 1 minus R to the T power. The only difference being that you're subtracting your rate instead of adding your rate. So that your base will wind up being less than 1 rather than greater than 1, which was the case in the previous two examples. But again, A is your initial or your starting amount. R is your rate, and just as before, that's as a decimal, so you're moving the decimal 2 places in order to use it in the formula. And T is time, typically in years. So example 3 says an investment of $12,000 is losing value at a rate of 4% each year. Write an exponential function to model the situation, then find the value of the investment after 9 years. So the function f of t equals, again, my initial or my starting amount is 12,000 times 1 minus, because it's losing value, 0.04 as a decimal to the t power. Now I want to find the value of the investment after 9 years. So f of 9 equals 12,000 times 0.96 to the 9th power. Now again, when you're going, almost to 0, when you're going to your calculator, you do not have to go ahead and add or subtract the values that are found within the set of parentheses, especially with the subtraction if that throws you off. I typically go ahead just so that I'm not typing in quite as much, but either way should yield you the same answer. So I'm keying it into my calculator the same way I did previously. Again, we're talking about money, so that's going to be $8,310.41. Something I do kind of want you to think about, though, when you look at a problem like this, because that number right there is less than 1, that is an indication that you are talking about exponential decay. You can think of this problem as either losing 4% each year, or you can think about it as holding on to 96% of the value each year. So I just want to point that out, because typically on a multiple choice test, you wouldn't see the 1 minus 0.04. You would simply see that 0.96, because that's the amount that you're holding on to each year. And then the last example on this side of your paper, Mark bought a brand new car for $35,000 in 2008. If the car depreciates in value approximately 8% each year, write an exponential function to model the situation, then find the value of the car in 2015. So that's going to be f of t equals, again, my starting amount or my initial value was $35,000, and that car is losing 8% each year, so 1 minus 0.08. And then my power is t for time. Then f of, because I'm trying to determine what's the value of the car in 2015. Since the car was purchased in 2008, I'm trying to find the value in 2015. That's 7 years after purchase. So I'm calculating f of 7, or plugging in 7 years. So it's going to be 35,000 times 0.92 to the 7th power. Again, that value of the car is losing 8% of its value each year, so it's holding on to 92% of its value each year. And just as the other 3 examples, plugging my information into my calculator, I'm going to round to 2 decimal places. Again, we're talking about money, the value of the car, and that car 7 years later is worth $19,500. $524.63. So those are some basic examples for exponential growth and exponential decay. The setup is the exact same. It's just with your growth, you're adding a rate, and with your decay, you're subtracting a rate. The next video will talk about compounding interest. But if you wanted to go ahead and get started on your homework, at this point you can go ahead and do problems 1 through 5 on your homework assignment.